Okay, we are back, and this is where we left in the last module, the absorption and emission spectrum of 7-aza-indole in hexane, N-hexane. It is difficult to get this kind of a result in protic solvents, because as we discussed in the case of 3-hydroxyflavone, in some other cases you would get block structures that are formed. So, hexane is a better solvent, and I am only showing you not even the tip of the iceberg, tip of the tip. There are hundreds of papers on this, where people have done temperature variation, quantum chemical calculations, different kinds of experiments, and it was more or less agreed already by mid 1995 that double proton transfer takes place here. And 7-aza-indole dimer has been studied by people who are not spectroscopists also, because it is a DNA base pair model. So, that biomimetic aspect is also there. So, lot of studies were there. For our purpose, what we need is, upon increasing concentration from 10 to the power minus 4 to 10 to the power minus 2 molar, small change in absorption is seen, but what is most significant is that this monomer emission goes down, and you do not see going down here because it is normalized here, and tautomer emission becomes very prominent between 400 to 700 nanometer, emission maximum somewhere at 480, 490 nanometer. This tautomer emission becomes prominent in at higher concentrations, right. And this is the starting point of our time resolved spectroscopic discussion, and this data that you see here is from this 1998 Jeffeschem A paper by Takeuchi and Tahara. So, what they started with is this. Starting point was very well non-ambitious, and I will show you another paper that was published by Zuel group before this 1995. So, there was some background. So, what they thought was this, that all right, this excited state double proton transfer takes place. We know that this non-proton transferred species, the locally excited state, has emission in 320 to say 400 nanometer region, and beyond 400 nanometer it is predominantly the proton transferred species. And there is another attractive feature. Look at the spectrum. This locally excited state emission gets over by 400 nanometer, and that is where the proton transferred species spectrum begins. So, good thing here is that there is almost no overlap. Since there is almost no overlap, the data are simpler. If there is overlap between the two, then there would be a significant region where you get signal from this as well as that. Actually, it is there, as you will see, but it is not very much. Okay. So, if that is the case, then as we know, then in the region of the non-proton transferred locally excited dimeric excited state, you expect a fast decay, and in the region of emission of the proton transferred dimer, you expect to see a rise. Okay. This is the expectation, and that is what they saw. So, let us go through the data a little carefully. So, 320, and these are not normalized, by the way, that is why you see difference in heights. At 320 nanometer, of course, that is the blue end of the spectrum, the intensity is really small. So, you see a decay. It becomes more and more prominent as you go to 350 nanometer, 380 nanometer. When you go to 420 nanometer, once again intensity is small, and you understand that if you remember the spectrum, 420 nanometer is somewhere here. So, just before and just after 400 nanometer intensity is small, but you have made the crossover already from the locally excited dimer to proton transfer dimer. And here you see it looks like there is that fast decay still there, but there is something that is very long lived, and that becomes prominent at 440 nanometer, 445 nanometer. At 455 nanometer, look at the data very closely. What are the features that you see? And look for features that are subtle. What do you see? I will give you the easiest. You see a long lifetime, right? But there are two other features. What are the two other features? Initial time, that fast decay is still there. That means some monomer emission is there, even though you do not see it really in the steady state, it is still there. Do you see the hint of a rise? Yeah. do you see that there is a hint of a rise here? Of course, the moment you go from 455 to 500, it is rise all the way, followed by a long lifetime. But the reason why I am spending so much time on this is that this is what you see, a fast decay followed by a rise when you see emission, when you are in the region of an emission spectrum where you have both. Generally, our expectation is rise. Rise is for the destination state, right, the proton transferred state. But since the non-proton transferred locally excited state also makes a contribution to fluorescence at this wavelength, these are two independent things almost. I mean, this grows from there, fine, but you do see the decay there as well. So, you can get data like this. So, in our JChemPhys paper of 2010, I think, in another system, 2,2-pyridyl benzimidazole, we observed something like this in upconversion. These are all upconversion data, perhaps do not need to say. So, after 455 nanometers, so this is something that you might get if you do an experiment, you should know, you should not ignore it. If you go more towards the, and you can see they have deliberately put in a gap, 455 and 500, actually they had recorded decays at many wavelengths in between also. But the gap is so that you see it nicely that there is a rise. So, what is this fast decay? Decay of the locally excited state. What is the rise due to? The rise is due to the formation of your proton transferred state. And this decay on blue end and rise at red end of emission spectrum is something that you expect if you work out this kinetics of a two-state model, where one state depletes and as a result of that the other state grows. You get a simple bi-exponential function where where the formation of the second species is associated with a negative amplitude and decay of course has positive amplitude, fine. So, qualitatively nothing very surprising, but when the decay was fitted, and this is where fitting becomes very important. As we have said several times earlier, you can fit almost everything to a bi-exponential decay that may be appropriate, may not be appropriate. In this case, they could fit the blue end decay to two components, 0.2 picosecond and 1.1 picosecond. So, they had to be confident whenever you go to bi-exponential fitting, there are still plenty of conservative people and for good reason who would start doubting your fit. That is how do you know it is not tri-exponential? How do you know that it is really bi-exponential? Because over parameterization always gives a better fit. So, one needs to be very careful, one needs to have a model in mind and one needs to be able to interpret the data correctly. So, 0.2 picosecond, 1.1 picosecond. Here Takeuchi and Tahara had some help from their prior work that we discussed in the previous module. They had already established that the time required for S2 to S1 conversion is something like 100 to 100 picosecond, 100 to 100 femtosecond. So, they were confident because they already had this kind of data in other systems. The rise was fitted to a single term. So, what they did is for this kind of a sequential process where you excite and then you have a first precursor, precursor 1, which makes way for precursor 2 with a time constant tau 1, then precursor 2 gives rise to P3 with time constant tau 2, which has a lifetime of tau 3. You have expression of fluorescence decay like this, which is not unknown to us in this course. I at time t after excitation is equal to k1 of lambda multiplied by p1 of t plus k2 of lambda multiplied by p2 of t plus k3 of lambda multiplied by p3 of t, which simplifies into our well known tri-exponential fit. A1 e to the power minus t by tau 1 plus A2 e to the power minus t by tau 2 plus A3 e to the power minus t by tau 3. The reason why we are showing this line even is to emphasize the fact that many times it is not enough to just fit your data and work with the amplitudes. you might want to do a simulation of the data. So, when I say simulation, I do not mean MD simulation, simple kinetic simulation, small code that you can write using MATLAB. You might want to actually work out the kinetics, and you might want to get these functions P1 of t, P2 of t, and so on and so forth. Eventually, it will be like this. So, I recommend that you go through the work of Flor Rodriguez Prieto. They have done a very efficient, very thorough Forster cycle analysis of the time resolved data of proton transfer in benzimidazoles. Well, pyridyl benzimidazoles. Forster cycle is something we have not discussed in this course, but it is there in Lakovich's book among other resources, quite easy to understand. Generally, when you have things like this, it is good if you can do a Forster cycle analysis in case of proton transfer and get greater insight out of your amplitudes and lifetimes. That is what Takeuchi and Tahara had done. What is K1 of lambda? That is the fluorescence intensity in lambda space, and of course, when you go from lambda to nu, you have to multiply by this factor lambda square. If you integrate K1 of nu over all frequencies, then that gives you an idea of the radiative decay rate. Radiative decay rate is the inverse of radiative lifetime. So, remember in basic courses of spectroscopy, we talk about Einstein's kinetic treatment of stimulated and spontaneous emission. So, hence we get Einstein's A coefficient and B coefficient. Einstein's A coefficient is associated, it is basically the rate constant associated with spontaneous decay. Inverse of that is the radiative lifetime that we are talking about. And you can get the oscillator strength. Oscillator strength, you might remember, is something that tells you how how strong the transition is. So, oscillator strength is has a simple mathematical relationship with other parameters like the experimentally determined epsilon, molar absorption coefficient or molar extinction coefficient, and transition moment integral, which is a theoretical quantity. So, oscillator strength is a more classical concept, and you can find it from this data by integrating K1 over all frequencies and dividing by 1 by nu square. So, this is something that you can get from the emission, and the premise of this discussion of getting oscillator strength from the emission, when you excite and when emission comes B1 equal to B2, B12 equal to B21, right. From there you can actually relate it to absorption as well, as we are going to say soon. So, hence doing all this from the time resolved data, Takeuchi and Tahara could construct the fluorescence spectrum of all the components. So, this is the fluorescence of monomer, not very difficult to find because it is there in the steady state. This is the fluorescence of tautomer, again not difficult to find because it is there in the steady state. So, that helps your time resolved data analysis also. Then in addition to monomer and tautomer, they identified two precursors, precursor 1 and precursor 2. Precursor 1 is at smaller wavelengths and therefore higher frequency, higher energies. Precursor 2 is at longer wavelength, therefore lower energies. And they established that the 0.2 picosecond time constant is the time associated with precursor 1 to precursor 2 transformation. 1.1 picosecond is the time associated with not only the decay of precursor 2, but also the rise of tautomer emission, and herein starts the debate. So, what they are saying essentially is that you have some precursor to start with, from which no proton transfer has taken place, no tautomer is formed. From there you get another precursor which is associated with a slightly longer time, 1.1 picosecond, and from there you get the tautomer. Okay. So, I will tell you why this was one of the starting points of the debate, but well, this we have said already that they also determined the oscillator strength. And to summarize the data that they had, this is neglect the first line for the moment, even though I have shown it to you. So, you already know the answer. They had these three components, right, 0.2 picosecond, 1.1 picosecond and like 3 nanosecond or so. Peak wavelengths are for the first one 330 nanometer, for the fast decay the species has peak wavelength, emission wavelength of 350 nanometer. This one, this tautomer emission 490 nanometer. Fluorescence lifetime turns out to be 0.2 picosecond, 1.1 picosecond, 3.2 nanosecond, and radiative lifetime turns out to be 13 nanosecond, 38 nanosecond, 160 nanosecond. Okay. What is radiative lifetime? 1 by Kr. Remember what is lifetime? Lifetime is 1 by Kr plus Knr. 1 by Kr is 13 nanosecond. 1 by Kr plus Knr is 0.2 picosecond. What does that mean? Means there is some very efficient non-radiative process going on here. That is why you do not get so much, because 13 nanosecond radiative lifetime is not actually bad, it is quite good. But due to this non-radiative process, it does not get a chance. So, remember I referred to this Einstein kinetic treatment a little while ago. One thing that is not included in that treatment is non-radiative process. In Einstein's treatment, you get to learn that spontaneous emission is a reality, and it is always there. We also get to learn that the rate constant of excitation is equal to rate constant of stimulated emission. These are the two important things that we learn from the treatment, rather simple treatment. But what is still not done there is this non-radiative rate constant, which is of utmost importance when you discuss ultra-fast processes. Okay. So, this is a very good piece of data also to sensitize us to the fact that non-radiative processes can bring about a sea change. If you can somehow stop the non-radiative process, then this species will have lifetime of 13 nanosecond. Suppose there is no non-radiative processes at all, lifetime will go up from less than picosecond to 13 nanosecond, and you will see a huge increase in fluorescence. You do not see it because of the non-radiative process. Okay. And the associated quantum yields, you know how to calculate them, A I tau I divided by sum over I A I tau I. For the ultra-fast component, it is 1.5 into 10 to the power minus 5, really very small. Fast component 2.9 into 10 to the power minus 5, marginally better. Slow component 2 into 10 to the power minus 2. Now, 2 into 10 to the power minus 2 may not seem attractive for somebody who is looking for a brightly fluorescent molecule, but then compared to 10 to the power minus 5, 10 to the power minus 2 is 1000 times more. Yeah. All right. Now, the oscillator strengths calculated from the fluorescence spectra, well, not fluorescence spectra, fluorescence data, turn out to be 0.13 for ultra fast, 0.048 for fast, and 0.023 for the slow component. And then if you add these two, 0.13 plus 0.048, that turns out to be 0.16, which closely matches the oscillator strength that you determine experimentally from the absorption spectrum. Remember what I said a little while ago, oscillator strength, generally when you say oscillator strength, you think of absorption spectrum. From there is a straightforward determination from epsilon. That turns out to be about 0.16. And when you sort of back calculate from the fluorescence data, it turns out that almost the entire oscillator strength is accounted for by excitation to the species associated with ultra fast and fast components. So, that means ultra fast and fast components together make up sort of a twofold excited state ensemble to which excitation is taking place. Remember, excitation that we do here is by ultra fast pulse. Ultra fast pulse is not monochromatic. So, if you have two states that are closely lying to each other, then you might end up exciting both together. Okay. So, this is the state of affairs here up to here, that oscillator strength is accounted for by excitation to not one, but two species. And what are the two species? Now, the first line that was written in the table, the ultra fast one was assigned to dimeric S2 state. The fast decay is associated with the dimeric S1 state. Why did they think this should be the assignment? Because they had prior knowledge that they in other compounds, they had shown that you actually can look at the emission spectrum originating in S2 if you look at ultra-fast time scales. Without that, they could not have achieved this, right. So, this was the assignment that was done. And the main contention here is that excitation is taking place to not one, but two excited states. One is S1, one is S2. What are these two closely lying excited states? What is the, do we have some additional evidence to support what has been said so far? We will take that up in the next module.